was halfway through building another video, and trust me, what's coming up is really fun. I've been having a great couple of weeks working on it. But while I was doing that, I got a box in the mail. We got a new set of magnets showed up for a project we're working on, and I don't think anybody's ever quite unboxed neodymium magnets this big before. So I've already started. I got halfway through unpacking the first one and realized, wait, back it up. I want to show this. I want to make a video about this. What we're going to do today is I'm going to show you what is effectively an unboxing of two magnetic rotors that are probably the biggest neodymium magnets that money can buy. I know I've alluded to having large magnets before, but let's show you how they actually get shipped, because I think that could actually be interesting for someone. Magnets get shipped typically in really big wooden crates like this. This is heavy. I can think this one's marked as 250 pounds on the crate. It's shipping 2 magnets. We've got something that ships a little bit bigger, but in general, magnets come in very large shipping containers because for 2 reasons. 1, you have to protect them and to protect things around it. But 2, there are certain rules that the IATA puts out for how do you ship magnets. And they're kind of guidelines. It has to do with compass deviations at certain distances from the outside edge of the case. But what you need to know is if you are trying to ship a magnet, the easiest way to do it is to put it into a large wooden container with a bunch of levels of steel shielding, and you'll get to see that, don't worry. So if you've ever seen, I'll maybe link to some other magnet unboxing videos like the big 6-inch neodymiums, but these are not the big 6-inch neodymiums. These are something different. I want to say significantly larger. Nails. To get at this thing, it comes with a bunch of these, it's plastic wrapped. Then we got the metal straps on it. Then we've got the nails that you take the pry bar and you pry everything off. But if you get down to it, we end up with steel sheeting. So the first layer that you find when you open one of these boxes is a big plate of cold-rolled steel sheeting. And you actually find 2 of them. And this whole box, and I'll edit this up so you can see it, the whole box is basically surrounded with cold-rolled steel sheeting. Now, this is unfortunately the part where I've already started taking out the one out of the other side. But when you do it, you end up with, now, styrofoam. And lots and lots of styrofoam. So the magnets we get come out of a city called Ningbo, which is where basically all neodymium magnets come from. It's about an hour by train outside of Shanghai. It's a fun place. I like Ningbo. These ones are from Tongchuan, I think. These are Tongchuan magnets. We bought magnets from pretty much every major vendor in Ningbo, so I think I've been to like all of them at this point. Anyway, these guys actually, I really like their shipping. They've got good materials. Some people do it differently depending on the size of the magnets, but these ones are gigantic. We'll put those there for now. Once you expose enough material, then we get down to a wooden box, inside a wooden box, inside a metal box. Okay, so when we get down to it, here's the top of our wooden box. The second box is additionally, when you open it up, it's just steel. It's just 1, 2 sheets of more cold-rolled steel. It's got to be cold-rolled steel apparently, and that just has something to do with the fact that it has the best saturation performance at DC. Leave a comment if you actually want to know how to build these things, because there's like a whole science that goes into it and it's very minimal. But you know, you too could be a magnetic box expert in under 45 minutes of learning things. I should put this on my LinkedIn. Okay, this is the part that I really love about Tongchuan. They ship with these like super weird plastic, weird plastic printed components. Have you not seen these before? They ship the E350s in these too. Oh. So I got a ton of these things. We should figure out what to do with these things.
Why do they put these things?
Spacing. It keeps the magnets spaced away from the metal. So the metal box, and it has to be a continuous metal structure, that's to keep the flux from the magnet kind of semi-contained, but you don't want the magnet to stick to the side of the box like the magnet wants to do. So they put these plastic spacers in, and they put in a lot of plastic spacers. Like this. Just plastic. I gotta find a use for these plastic spacers. You know, there's another YouTube comment section video right there. Once you get down to this point, we actually have to take the magnets out. Okay, so at this point, okay, oh, there we go. Okay, we get it up on the end. So if, oh wow, actually that's not so bad. Once you get it under there, so this is the last stage of shipping. It's basically just, what is this? It's not bubble wrap, it's just like foam wrapping around this. I did not plan this well enough. Hold on, I'm gonna just put that there. It's not going anywhere. It is now firmly stuck to the outside edge of the box, but we need to find a space for it. I'm gonna put it over on the other side. So now, once you get down to this part, now we start to get to the fun of this, because this guy sticks, and it sticks pretty hard. Like just, there you go. That's, this is almost not metal as well. Do this with a hammer, and there's a little bit of a difference. The problem is, you still need this because now you have to cut this. So we have to be super careful. And it's already starting to pull it out of my hand. So let's just work our way down. We want to cut through the foam, but we don't actually want to cut all the way into the magnet. Not that I really care. You can't, these are hard to scratch. When you scratch them, you'll know. I hope that they used the cool epoxy, but I don't think they did on these ones. Now we get down to the bubble wrap layer, and the bubble wrap layer is the extra special last version. Maybe I can take this apart first. Let's see if I can pull. And the only reason I can do this so carelessly is because I've checked to make sure there's nothing metal around here. Oh yeah, this thing weighs like 20 kilos, by the way. This is a big, big magnet. And this is actually for a different project that is an active project, so we're not going to be doing anything crazy with this magnet. Unfortunately, this is as good as we're going to get to put it on YouTube. But in general, yeah. Okay, here we go. I'm going to try a couple more layers of bubble wrap here. Now, I can actually feel that I'm just touching the surface, which is probably okay. Yeah, I definitely left a line down there, but that's all right. Here we go. All right. I wonder which camera is going to get the big reveal. Here we go. This is, looks like a steel cylinder, because it actually is a steel cylinder. A solid, oh, there's an axle sticking under there. I gotta get a little bit more. So here we go. Let's just pick this up, and here is a solid piece of neodymium. I actually don't know how much it weighs. I could figure that out, and I'll throw it in the description of the video because I don't want to keep recording this. But in general, here it is. Now this is a Gauss meter. It measures magnetic flux, and the probe at the end, it just uses Hall effect, I believe, to measure the strength of a magnetic field. We get it in millitesla, because I prefer millitesla, which is just Webers per square millimeter, give or take. Where is this thing? There it is. Okay. I think it would be better. Forgetting, of course, it's been a while since I've dealt with these big magnets, so I keep forgetting that, yes, absolutely everything is going to stick to it. To the surface. Now somebody, and by somebody I mean the good folks at Tungtron, have marked along the surface. So if we take our probe tip and we touch it ever so slightly to the surface, we're getting about 4.2, 4.3. I saw a 4.4 there, negative 4.4. If I reverse this, I get 4.3. Yeah, okay. We're going to do it just so I get a positive field. And you'll notice that it is positive and negative. Literally the only thing there is because of the way it's placed on the magnet. 4.1, 3.9, 4.43, 4.45, 4.7, 5. Oh, this is better. 5.2 all the way across. 5.2. 2, 5, 1, 5, 2. Yep, this is good. This is what it's supposed to be. We should have, 5, 4. Well, okay, let's pretend that 5, 2. Seems to be fairly uniform running across. 5, 3. My hand is not uniform by any stretch of the imagination. 5, 5. Oh, look at that. 5, 6. 5, 8. And brought back to 0. So if we rotate now here, 0. That's very interesting. I can describe this, but if you have thoughts why I'm getting near 0 field at the surface of the magnet here, please leave a note in the comments for all you aspiring magnet scientists. I will absolutely explain it in a second though. I'm going to give you a second to figure that out while I rotate this. And now, 6, 5, 9, 5, 8. Notice it's negative. We haven't moved the probe. I can do a continuous cut so you can see this, but I haven't moved the probe. The probe is still in the same orientation as it was before. Now I'm getting a negative field that's actually a little bit stronger than the field before. Ignore that. I mean, we can measure what the peak field is, but in general, I'm not too concerned. If you haven't left your guess as to why I'm getting negative fields now, leave a comment. I will publicly acknowledge anyone who gets it right in the next video. Not the next video. The next video is nearly done, actually. 1, 4, 2, 2. Yeah. Now, I'm going to try something, and maybe this will give a little bit of insight. Now I'm going to turn it sideways. Oh, is that going to change anything? Nope, that doesn't change anything. 0.3, 0.5, 0.05. Yeah, does not change very much. Now we're going to try something a little different. Now I'm going to rotate it sideways like this. 0.37. Okay. 0.47, 48. So take what you know about magnetic fields, try to extrapolate it, draw some pictures, let me know why we see a field profile like this. So let's go back. So if we're going to figure out what's happening with our magnetic fields and why the Gauss meter is measuring such a different field going around the surface, we have to talk a little bit about magnetic fields in space. And to do that, I brought a magnet. Now, this is one of the magnets that we used for the magnet smasher. I would say that without buying really expensive custom tooling, it's kind of the biggest magnet you're going to get. This is a Neodymium N45. So the magnets we were looking at had a pole up here, I'll just draw on it, and a pole down here. And what we were measuring is we were measuring the field at this point, we're measuring the field at this point, and that's where we're getting our plus and minus 3 to 500. 2, 5, 1, 5, 2. And then we were getting a field at this point and this point, and that's where we're measuring 0. So 1, 0 Tesla. Why is that the case? A magnetic field exits from one side, we'll call that the North Pole because that's what people usually call it, circulates back around and comes back into this side. Line, it's going to circulate around this way and circulate back in. And as you go farther and farther out, you get more and more field lines that exit from one side and back to the other. Now, if we look at it though, we've got a point right here where all the field is coming out, or most of the field is coming out. That's the strongest part of the magnet. That's what we call the pole. That's why you hear about the North Pole of a magnet. Well, really, that's just the point at a magnet where all the domains are lined up at the surface. And I'm not going to get into surface demagnetization effects because that's like an entire series of articles. You can do an entire PhD on surface demagnetization effects in complex magnetic structures. The magnet doesn't have some sort of special property that makes this part of the magnet north and this part of the magnet south. You can change that quite easily. In fact, in hard drive, you change that all the time just by writing to your hard drive. What I'm going to say though is we'll call it north and south for the time being. Just know that north is where the magnetic domains are aligned with the spin in the right direction to cause the field to exit. So I'm going to use this whiteboard marker as my Gauss meter approximation. So it's a flat rectangle. And what we're going to say is up here, I'll draw on it, that is our flux direction. So this is where we're measuring it. So if I put the Gauss meter, whiteboard eraser here, we're measuring the flux traveling up, out of the magnet, into space. If I measure it down here, we're going to be measuring all the flux that's traveling in this direction. And if I measure it down here, we're measuring all the flux that's traveling in this direction. But if I turn it, now we're measuring the flux traveling in and out this way. So at the top, we've got maximum flux. This magnet is pointed in this direction. All the flux is coming out here. We put our Gauss meter probe there, and all the field is going through our probe. We're not measuring any field in this direction, and we're not measuring any field in this direction. All the field we're measuring is in this direction, and all the field coming out of the magnet is in that direction. If I rotate my probe now, like we did along the surface, and I measure field coming in this direction, not this direction, not this direction, we see nothing, because all the field, all these flux lines that I've drawn are now pointed straight down or straight through in a direction we're not measuring. If we rotate it back down again, like we did, now all the field is coming through the bottom here. It's coming into the bottom of the magnet, and that's what we're measuring, this big negative field. So in here, all the field is going this way, but we're trying to measure this way, so we're not getting anything. Then when I turned it again the next time, remember, we had all the field going in this direction again, but we're measuring it in this direction, so we didn't get anything. Third measurement, though, is the one where I rotated the probe tip this way and put the probe tip perpendicularly to the surface. Now we're finally measuring all the magnetic field, and we can go back and I'll try to edit all that in so you can see it. We're trying to measure the amount of field going in this direction. If we rotate it, now we're trying to measure this field, but we're only getting field in this direction, so that's why it doesn't work. And the same thing, now we're measuring field here, but it's actually coming in this direction, so we get a negative field. So that's why when we did those initial measurements, we saw a really high field here, but zero field here. It's not because there's no magnetic field, it's just because we're measuring the wrong field. We're measuring something perpendicular to what we're actually seeing. Here, we have a magnetic field that is pointed up in this direction. And it's up, 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 until we hit the surface of the magnet, and then it flips, and we have a very strong downward field. And that's because we've moved from the internal magnetic field, which is all pointed in one direction, to this external field, which is now pointed in the other direction. And there are reasons that you're going to want to care about this, because if you're trying to calculate the magnetic field, say from this point to this point, and you measure across there, and you sum all the magnetic fields, you're actually going to find that the field in here gives you a really strong upward positive value. The field out here gives you a very strong downward negative value. If that was your answer, good job. If that was kind of your answer, good job. If you tried to answer it, good job. That's the beginnings of being a scientist, questioning why something happens, giving a hypothesis, and then testing it. Hopefully this was a fun few minutes here. Thanks for watching. If you like what you see, hit the like button, hit the subscribe button. I do have another video that is in the pipe. I should have it out in the next week or so. It is something very different, something much more involved. And in the meantime, thanks for watching, and I will see you in the next video.